All right, good afternoon, everyone. Right, so Fabio is going to be talking today. He's a senior principal architect at Red Hat. He's going to be talking about composing systems in an automated way with Ansible, Podman, and bootc. So over to you, Fabio.
Thank you. So what we are going to talk about today is, as I said, bootc, systemd, and Podman, Ansible, all these things and how they can work. But we will start with why, and then also move to bootc and then all the other pieces. So very quickly about me, I've been working in IT, mostly sysadmin kind of roles for the last 20 odd years, and I've done a lot of things that were pioneering at the time. So for instance, I started to use Ansible in 2013. That was 0 point something, the version of Ansible at the time, and immutable systems since 2016, which at the time was bleeding edge stuff. So I really like these bleeding edge things. bootc is not that bleeding edge nowadays, but I think it's still in the infant phase, which I think it's even more interesting. So some quick disclaimers. Everything we are going to discuss is fully open source. It's available in the community version and also in the enterprise versions if you want to buy enterprise versions. It's same thing. It works exactly the same. Everything we are going to discuss is architecture independent. It applies to every architecture, so you are not bound to x86 if you don't want to. And Linux is required. And by Linux, I mean a Linux system that has at least Podman and systemd. So why? Because in the end, we are going to talk about containers and running containers in a different way. So why not Kubernetes? Kubernetes has been the answer for every container problem. So why not? First of all, Kubernetes is heavy on infrastructure. So if you can avoid that, that would be awesome. Second, it does have a steep learning curve. It's not that easy as it seems. And also, it's very complex to manage. Even if you are able to spin it up in a reasonable amount of time, then maintaining it over the course of months, years, or decades, it's going to be very complex. So the reality is that there are some problems that are Kubernetes shaped, as I call them. So effectively, where Kubernetes is awesome at doing those, at solving those. So for instance, if you have to provide a container as a service to someone else, either or internally in your organization or another team or external to your organization, then Kubernetes is going to be the API that they are going to expect. So obviously, better to have Kubernetes. Second, if your deployments need horizontal autoscaling, that is what Kubernetes does, so probably you will want to have Kubernetes. If your container needs to be auto-placed on different machines based on workloads or other logics, you might want to look at Kubernetes. In all the other cases, I think you should really consider not using Kubernetes. And here we go to the other option, one of the many other options that we have, which is what we are going to talk today. So the first part will be about bootc. If you don't know what bootc is basically a set of tools to make an OCI container image, so effectively a container, into an operating system, a full operating system. So the way it works is that the logic would be to bridge that difference that is between the easiness of container deployment and the problems that hardware or VMs actually have. And it does support atomic updates as well as rollbacks for the whole system, because as you have the atomic updates and rollbacks for single containers, since we are using containers for whole systems, then you get all those advantages on your system. And it does leverage all the usual tooling that you are used to with containers, because in the end, we are talking about a container that is a little bit special because it does have a kernel that usual containers don't have. But for all the other aspects, it's a simple, normal container. And which also means that it's going to be very easy to create CI/CD to actually test your container, because in the end, it's still a container. So everything you do in your CI/CD, and hopefully you do test your containers in CI/CD, you can actually use the same pipelines to also test your base image. So how does immutable Linux work? Because in the end, a container is immutable for some definition of it. So how does that translate when we have an operating system? So the operating system file system is mostly read-only. And mostly read-only means that, for instance, the folder /var is going to be variable, so mutable. But basically all the rest of the operating system is going to be immutable. And then there are some mount points such as etc, which usually are real folders into the main / folder that are going to be mounted from /var so that they can be mutable. So there are a little bit of tweaks, and there are multiple folders in the end that can be modified, but a lot of folders such as /lib, for instance, /bin, and so on, are completely mutable. OS updates are atomic, as we discussed before. Since it's container, you do download the new version of the container, and then you reboot basically in the new version. So it's either you are on the old container or you are on the new container. You cannot have an intermediate status. The operating system can be reverted because having the previous container available still to be booted allows us to either boot in the latest version, the last one that we downloaded, or the previous one that we had. And potentially you could have more than two if you really need to. And also, all the user environment application run in isolation, usually in layer containers. In theory, you can run them directly into the operating system itself, but it might be not the best choice because it would make your whole system way more complex. There are some things to remember about this whole thing, which is how structurally it works. As an input for all this tooling, we are going to get either a Docker file or a container file. Those are exactly the same things, two different names, but same things. And we will get out an OCI image, exactly as for any other container that you have in your organization. bootc is going to be the tool that converts images, container images, into bootable file system. Then, as an artifact from bootc, we can get disk images, various kinds of those, ISOs, or we can do direct installs directly from bootc. So effectively, if you have already a way with PXE-boot, for instance, or those kind of things where you require an ISO image to deploy your systems, you can still get an ISO image out of this. Runtime, we have full systemd if you obviously have it into your image. If you don't have systemd in your image, well, that's going to be a problem. But for the second half of the talk, from a bootc perspective, it does not care. It will run whatever PID1 is in your image, and it will work that way. And the life cycle, every time you have a new image, a new version, you create a new image, and then you switch to that image, reboot the image, and then eventually roll back if something went wrong. So minimal base images, because usually in container world you do not start from scratch. You can do it, it's very complex and it's error prone, so usually people don't do it. Obviously you can do it as well here, but usually what you would do is start from something already existing. So Fedora, for instance, has a Fedora-bootc image. You can directly pull it. It's exactly like the normal Fedora image, but it also has the kernel and all the other tweaks that it needs to actually become a bootc image. But if you don't want to use Fedora, that's perfect. And you can have a number of other distributions that have also bootc images already available. So you can pick any of those, and then obviously the list is actually way longer, but those are the most common ones, I guess. So how do you add packages to this? It's very easy, because in the end, this is a standard container file or Docker file, so exactly as you would do in that case. And in our case, obviously it's going to be in the image build, and we can use everything usual. So for instance, dnf-y install, and then whatever packages you want. Now, it's important to clean up stuff when you do images. This is not about bootc, is in general about containers. Clean up your caches, otherwise rebuildability becomes a little bit more complex. And by the way, -ipson is mandatory, so agree on the installation, because this is not going to be interactive, therefore without the -ipson it will fail. Some warnings about here, this: never use updates or upgrades. The reason is, if your kernel gets upgraded, your image will not boot. There are issues for that and reasons for that. Hopefully at a certain point in the future that will be fixed, but at the moment this is the current state. And also, if you do this, by the way, you are breaking completely the rebuildability of your image. You can update a single package if you really want to. That's not a problem, as long as that package is not a kernel and is not depending on the kernel to be updated. How can you add services? As usual, you can do whatever you want into the container file, but since we are talking about systemd systemd units are going to be the easiest way. And the way to do it is very straightforward. If you think about, you just create a unit, and then you simply copy it to the folder, and then you can add the run command to enable it if you want to enable it at boot. So very straightforward, nothing rocket science. You can also add users in this, and you can also use systemd to add users. There are many ways of adding users in a Linux system, but systemd is by far the best one in this context because it's way more aware of everything that is going on. So the way you would do it is, in this case, I've obviously added my user. You would just create a file that is called sysuser-your-user. .conf that has this structure. So basically the first character of the line identifies what you are going to do. So a U is adding a user, a G is adding a group, M is associating a group to a user to a group. And then obviously those are the usual parameters that you would pass to any user add or similar utility. And then the only thing you have to do from your container file is copy your file into /user/lib /sysuserd / whatever it's your user.conf. And there are also documentation on the free desktop, so it's very straightforward to actually understand all the possible parameters, because those are not the only three. There are like 10, 15 different parameters that you can use, so it's very convenient to read the whole documentation first. A warning about this. So many people add users in this way in containers. That is not a good way to do it. The issue is that you will get different PID, user ID and group ID potentially at every time you rebuild the system, which is probably not what you want. Now, in normal situation, this is less of an issue because usually you are running not on the container that you are building. So effectively, you would have a UID, GID mismatch between your host operating system and the system that you are building. So it's less of an issue. But in this case, this is going to be a bigger issue because you can then rebuild the container from the container itself, which then will obviously shift by one all the user IDs and group IDs, which becomes a big issue. While in the previous example, we forced the number of the ID, so that's not going to be a problem. You can also add user files or potentially any kind of file, but user files are the most convenient, most usual one in this kind, because for instance, you might want to deploy an authorization key to ensure that you can SSH into this box. With usual containers, that's less of an issue because you would not SSH into a container. You would probably go from the system below it to the container itself with the Podman exec or those kind of things. But in this case, obviously that's not going to be possible because we are talking about the underneath operating system. So we can still use systemd, which is great. And we would create another file, another configuration file, which is similar to the previous one, as you can see. The logic is exactly the same. You would have these weird first characters that define what the line actually is going to do. And then you have all the various parameters that identify the exact operations that you want to happen in that step. So in this case, we are going to create a couple of directories. Obviously, the first one is my home directory. The second one is the .ssh directory, and then I'm going to replace the .ssh authorized key file with my SSH key. And also notice the fact that I'm basically performing a chmod 700 on the folders and a 600 on the file itself, because otherwise SSH will complain about files being too open and that kind of things. Then I also have Z here, which is for system for SE Linux. Every time you see a Z in system in Linux, either capitalized or lowercase, that's always SE Linux. I'm not going to talk much about SE Linux because SE Linux is hours of workshop, but this will allow you to basically retag like a restore con /var/home /fale. As you can see, also my folder is not /home /fale as it usually is in any system, but I have a /var in front. The reason is, as I was mentioning at the beginning, in bootc systems we do have a lot of folders. All the folders that should be mutable, such as home, are mounted from /var, so that basically /var becomes the only variable file system on the whole system, and then everything else is just symlinks to that one. And then obviously we copy the file into the right folder where systemd is actually expecting it to find it. And the way this whole thing works, this one and also the previous one, is that at every boot, systemd will check all those folders and ensure that that state is consistent. So that whatever you do, let's say that you boot your system, you remove the authorized key, and obviously you don't have it anymore, but as soon as you reboot the system, then your authorized key will respawn in exactly the same position and same content, which also guarantees you that it's going to be very hard to be locked out of the system. Yeah. This also has documentation, obviously. Now, there is a great feature in bootc, which is linting. So you can run bootc container lint into the container file itself, so that basically bootc will check if whatever you did is sensible, or if you did something that is completely out of bound. In that case, it will obviously error out, and then you can choose how to progress from there. So now that we have the container file, how do we build it? So we can build the container file and get the usual kind of things. We can keep tag semantics for safe rollouts. Yes, you can use latest or that kind of things. You should never use latest, not for this stuff, not for your containers, the other kind of containers. It does have a huge amount of implication. Use latest or stable or whatever you want to use. Please use versions stuff. And the way you would build it is very simple. Sudo, or sudo if you need to do sudo, otherwise you can also do a build without sudo. Podman build -t, and then whatever your image wants to be, and then the final dot is just for the location of the container file. So this is exactly the same way you would build any other container in your system. Now, usually the way those container file will look like is going to be that you have a lot of runs, a lot of copies, and so on, which means that probably your container will have tens of layers, which could be good, could be bad. It depends on how exactly you distribute it. But if you want to prevent that, you can squash the layers. So effectively, that means that all the layers that you declared into your container file become one big layer. And then you have obviously the layer that is the image that you are pulling from. So Fedora core was my case. And then one more layer of all your customizations. And obviously you can also create multiple container files and daisy chain them. And then Squash would create one layer for every container file. So you can play with that to ensure that you have the number of layers that you actually want to have. Now, how do you publish a new version? That's very straightforward. As it's a container, you copy it or push it to a container registry. So a Podman push image, and it will move to the container registry. Also, if you do this, it will not really work. You will have to have, instead of localhost, the right location where the container should be pushed. And notice the fact that by default, all bootc images have an out updater, which means that every number of hours, I think it's 1 hour or something like that, they will check if there is a new version into the repository, and if there is a new version, they will pull the new version and reboot themselves. So effectively, this means that you can easily upgrade all your machines. Now, if you don't want to do that, there are tricks for that one as well. Obviously, you can use different tags. You can disable the service that does that. You can inhibit in multiple ways. But be aware that that is a core feature of the system. And by the way, you can also write some tests, so effectively some scripts, that you would deposit into a specific folder of bootc, and at the boot, it will run your script. If your script will fail, it will roll back directly to the previous version to ensure that obviously you can check that your system was green before continuing, and if not, you can roll back. Now, we can also build ISOs, as mentioned. The way you do it is fairly straightforward. And basically you run, I always have sudo in front of my Podmans. The only reason is that due to the configuration of my machine, I cannot run Podman on my user. I have to run it as root, but also you can run it without sudo. So the way you would do it is basically use this container, this bootc image builder container, and then you would pass it all the storage of your containers so that effectively can pick up your image, and from that create your ISO. You have to specify the rootfs, for instance, if it's not already a pre-configured one, and a few other things, but in the end it's the usual parameters that any Podman run command would accept. Also, this is the documentation for all the possible parameters that you might want to use. You can also create a bootable image, so effectively a raw image or those kind of images. Same process as before. The only difference is that the type, it was ISO before, now it's QCOW, for instance. So this allows us to create both ISOs, which usually are more useful for bare metal machines, but also QCOWs and all the other supported formats for VMs, which it's way more convenient. And then obviously documentation as before. You can also obviously run one of those images. In this case, I run it with QEMU. Better to accelerate, couple of cores, 4 GB of RAM, and then you would simply use the QCOW image as snapshot and then boot from there. This is more for testing purposes than a production one. Hopefully you are not running your production system with QEMU. You can also install a bootc OS. You have multiple ways of installing it based on the fact that you are already running bootc on the machine, or you are not running bootc on the machine. The machine is booted or not booted, but this is the way I usually run it, where basically having a machine that booted Linux and has Podman available, you can hijack it and transform it into whatever you selected here to be your image. And here you can also inject SSH keys if your if your container image did not have an SSH key. You can inject an SSH key. This is going to be the root SSH key, obviously. So atomic updates and rollback, how do they work? You can manually upgrade. As said, there is the automated process in the background as well, and you can roll back. This is basically how it works. If you run it without the -- apply, it will just download the content, but it will not reboot. And due to how bootc works, until you reboot, you are on the old version. As soon as you reboot, you are on the new version. That's why the -- apply is there. Yeah, and obviously everything is atomic, so fairly straightforward. It's possible to switch to a different image as well. So let's say that you have, for instance, a base image that was based on Fedora. You want to move on a base image that is based on Ubuntu or vice versa. You can do it with one command, which basically means that instead of reinstalling your system, with one command you can change distro or potentially upgrade distro or do downgrade or whatever you want to do. So a few suggestions from experience. Base OS image, better to keep it as slim as possible without too many stuff on top of it. If you need to have different flavors, let's say for different application, maybe create different leaf images basically depending on your base image. Keep image single purpose. Try not to have one image that works for 50 different kind of workloads. Good thing is that we are now, just after this one, we are going to talk about workloads. And if you abstract completely workloads, then you are fine. But there are some cases where you might want to have, for instance, one daemon that is available on certain machines, but not other machines. And that's need to be like baked into the operating system itself, have 2 images for those. Prefer deterministic packages, sets, and config. As mentioned before, updates even of a single package is not suggested because then you are losing that deterministic flavor, which means that your image is not going to be rebuildable. And then automate the process. This is a fairly simple process. It was a Podman build process in the end. So any CI/CD tool that you are using to already build your containers can also build this one. So now that we have the base operating system, how do we run applications on top of it? And I think the best solution is leveraging Ansible, Podman, and systemd. How? So first of all, what is Podman? Podman is basically Docker, a reimplementation of Docker that can be either rootful or rootless based on how you want to run it. So effectively, you can run it as root, as Docker, or non-root if you want to. It has been donated to the CNCF in November 2024, so it has been a little bit more than 1 year since it left Red Hat space, and now it's available for, it was already available for everyone, but it's now completely safe into a foundation. It does have some key features. Also, the compatibility with Docker CLI is complete. It does have native support for OCI containers and native support for Kubernetes objects. So if you want to also run Kubernetes object, because for some reason you already have it and maybe you are deploying some application on Kubernetes and you also want to test it or run it on Podman, you can simply use the same usual Kubernetes object to deploy it in both ways, in both systems. What is systemd? Hopefully everyone has experiences with it, but basically is PID1 in the majority of distros. So effectively is the first application that gets run after the kernel, and it's going to be the application that's going to manage every other application that is going to run on your system. So it controls processes, services, dependencies, but actually way more stuff than that, because you can also do file system, users, as we have seen before, and so on. It does replace all older init systems in the majority of distros, not all of them, but that's the idea. It has a lot of interesting features. One is that it's built to manage long-running processes, because basically that is the definition of a service. It supports the dependency management, because that's its core value, I would argue, and provides a robust system of logging, which is journal CTL, journal D, and then you can query it by journal CTL. And interestingly for us, it does allow extension for custom kind. So by default, systemd has no knowledge of a container, but you can extend it somehow. So why use systemd for container management? Simply because it allows us to manage containers exactly as we would manage services and leverage all those features. And also, it does simplify the startup, shutdown, auto restart of the container, because that is exactly what it's doing with services. So what is Quadlet? Quadlet is technically nowadays a feature of Podman, but that's a technicality. It's a system helper for systemd by Podman. And basically, it allows you to create systemd units, or to make systemd aware of container units and to run them, which basically means that we can use containers as if they are first-class citizens into systemd itself. So, and yeah, technically Quadlet only exists in code and all documentation, but the feature is there. So key features, it does use declarative configuration of container management, which is very good because Ansible is very good at declarative stuff. So that can be very useful for us. It does support auto restarts, for instance, dependencies and so on. So effectively, we can have very complex architectures simplified a lot by the system, and enables seamless integration with any other systemd service, which means that we can have a container that depends on a service, or a service that depends on a container, or both, which helps because not every services that you have is going to be in a container, or vice versa. So why Quadlet removes a lot of complexity from managing Podman containers via systemd. You can actually use systemd and containers with I think it was Podman systemd create something common, which generate, yes, thanks, which was very weird and created very weird commands. This is the easy way and clean way of doing exactly the same. And reduce the need for manual stuff. I don't like to do things manually, so this really helps me. And it's ideal for persistent applications that are containerized, exactly as for services. So a base example of a Quadlet is this, where basically we have this is like a systemd kind of file. We do have the category container, container name, image, and I have a working systemd container, let's say, or Quadlet container. We can obviously add a little bit more stuff. So for instance, the install wanted by default target means that it's going to be started at boot. Now, the strategy to manage this is very easy. We are going to place a file into the right folder, reload systemd daemons, because systemd needs to regenerate obviously all its derivatives units out of the file that we just created. And then we are going to start and enable the daemon, which, by the way, is exactly the same process you would do if you are creating a service natively on a systemd system. If you want to do it with Ansible, this is the way you would do it. So it's exactly the same commands as we just discussed. We are going to copy the file, myservice.container. It's going to be my example in /etc/container/systemd, and then obviously the name. We are going to register a systemd daemons so that we can then check it. And so effectively, if the first file changed, we can reload the daemons without having to reload them every single time. And then there is also the part that starts and enable the unit. You should also have the handler for the restart, so that basically if the first one changes, you can notify the restart, which means that every time the container file changes, you are restarting to the newest version. But as you can see, I don't know, it's probably 20 lines of Ansible code, and we have deployed a container, and it's already started and running at every reboot. Now, we can do things a little bit more fancy if we have, for instance, dependencies. So in the same unit file, container file, we can add a unit section which qualifies which are the dependencies of it. So in my case, the container needs to be run after the local file system have been initiated, as well as the Nebula service is running. A Nebula service, in my case, is installed on the system itself. It is a native service. So we can obviously do that kind of cross system service container dependencies. We can also specify environmental variables, because that's a very common way of doing things in container land. So the way you do it is very straightforward. Into the container section, we can add environment equal name of variable equal value, which is very straightforward. And obviously you can have multiple if you have plenty to declare. We can also publish ports, exactly as you would do in a normal container setup with -p on Podman. We can use publish port and then specify the port that we want to publish. So in this way, for example, we would map the internal port 80 of the container, because maybe it's an HTTPD server or whatever I have into the container, to the port 8080, which means that we are really getting, from an external point of view, this really seems like a normal service on the system that is running on a port and everything else as usual. We can obviously also mount volumes. So the same thing as before, like with the -- volume, I think it's the option on Podman. You can also bind volume to the system. So effectively, this really becomes very similar to that service, native service that we described, which means that we can have that base image, bootc image, that is going to be equal maybe for all our machines, and then have different services running on top of them in containerized way, which is completely atomic, if not obviously for the volumes, for instance, that you cross mount, which obviously will have will create some holes between the operating system and the container. But aside from those, you would have that very nice scenario. And at the same time, we can manage all the underneath operating system as if they are exactly the same, because from our perspective, from a system operating system perspective, all your machines are the same, are just container platforms, or nodes where containers will be run, which means that probably you will have a very limited amount of bootc images around that is going to be very easy to update them, patch them, and upgrade them, because in the end, as long as they can run a container, all your application will continue to work. And then obviously if you have a new version of a container, because someone released new code, that's not a problem. You're going to tag it, as you probably are already doing it today. You are going to rerun the Ansible playbook to redeploy the newest version of the systemd unit, and then everything is updated. So wrapping up, Kubernetes is very good if you have a Kubernetes shared program. If you don't have a Kubernetes shared program, Kubernetes is not the good solution for you. bootc offers a very reliable, secure, and stable operating system, and that can be very useful to run container, potentially also to run any other things, because you could bake all your applications directly into the base image. You can do it. Is it the best way? I don't think so. Might be for you. Depends. It's one of those things that those are all options, and then you have to pick the right one for the specific case. It's very easy to create distros with bootc, as we have seen. It's like you start from a bootc distro that is already present, you add your changes, and basically you have a new distro or a new flavor of the distro, if you prefer. Ansible and Podman can be great to run containers, thanks to systemd and its facilities. And the whole thing is very straightforward, I think. So, any questions? I see one there.
With the bootc containers, are you able to install like kernel modules in them for like graphics drivers or storage drivers?
Okay, so the question is, can you install kernel modules for graphic cards or similar things into bootc containers? And the answer is yes. The only thing is that you might, in that case, if you are messing with the kernel, could be easier to start from an image that does not have a kernel already, so a non-bootc image basically, and put your version of the bootc of the kernel that you want. Only exception is if that module is already packaged, like in Fedora there are some RPM packages for NVIDIA modules, for NVIDIA drivers. In that case you can simply install it and it will work.
Thank you.
So I have a question. What would make you choose bootc over Fedora CoreOS, for example?
What?
Are they similar and also deployed with the systemd and Podman?
Yeah, so the question is, what would make me choose bootc over Fedora CoreOS? And the answer is, you don't have to choose, because Fedora CoreOS is bootc. So bootc is the technology that allows Fedora to create Fedora CoreOS as is today.
But then a follow-up question. Can I also then configure the file system and other things in bootc?
Can I also configure the file system and other things in bootc? Yes, you can. In the phase where you are building the ISO or the QCOW, or when you are installing, if you are doing a direct install, then you can specify all the possible file systems and parameters there.
Thank you.
You show us that you use Ansible to copy the Podman file.
Yep.
Can you do directly the container files of bootc?
So the question is, in my example, I showed to use Ansible to copy the container file. Can you directly add those at the build of the container file itself? Yes, you can. The consequence of that, though, is that if you have different applications, maybe you have some machines that need to run some Java stuff and other that needs to be HA proxies and others that need to be databases, then you need to have different bootc images, which could be a good side effect for you or a bad side effect. It depends on your specific configuration and installation.
Is it possible to force Quadlet to spawn a container from the Podman compose file?
Is it possible to force Quadlet to build to spin containers from container files? Podman compose files. Not at the moment. There is a bug open to do exactly that.
I have two, but you mentioned efficiency and squashing. My question is, I have a couple of machines that are on a remote line, data's metered. If I don't squash, so you keep the layers, do they gain efficiency if I just change a late layer?
So the question is, if I do not squash, what happens if one of the top layer changes, basically? Do I get, can I reuse all the other layers that are below that layer? Sadly, no. Because every layer has the hash of the previous layer, which means that if your first layer changes, all the other layers change as well.
Yeah, I meant the other way around. If the base remains the same, but if I change one file that is added late in the Docker file,
okay.
only that delta.
Yeah. So and conversely, all the layers that are below the layer that got changed can be cached and reused. Yes.
This seems like a great way to reduce drift. Would you recommend using something like this for workstation management?
This seems to be a great way to reduce drift. Would you recommend it for workstations? My laptop is using exactly that system. Okay. So, personally, yes.
And then a follow-up question: would it be hard to integrate with something like Active Directory through SSSD?
Would it be hard to integrate with Active Directory through SSSD? it would be as hard as it's on a standard Linux system. So if it's easy to integrate with your Active Directory, then it's going to be easy. If you have a weird Active Directory, sorry for you.
The QR code URL doesn't appear to work.
The QR code does not work. It will work in half an hour.
CI/CD.
Exactly. Yes?
Me? Yeah. I have an existing base of systems that have been made 4 years ago using RPM OS 3. Can I rebase to bootc without having bootc on there using RPM OS 3?
I have a system that is based on RPM OS 3. Can I rebase with bootc? The answer is yes.
Cool.
And if it's a Fedora RPM OS 3 system, and you try to type bootc, you will discover that bootc is already present.
When was it introduced?
Then it was introduced in, I believe, Fedora 42.
Ah, I'm on 37 with those. But
Okay.
I can
so-
upgrade those first and then maybe rebase to your stuff.
Yeah,
Okay.
or reinstall if needed.
Yeah.
Thank you all.
Thank you.